So, is everyone fine here with screen sharing? Can everyone see the slides?
Yeah, looks good.
Looks good.
All right, thanks. Okay, so it's hopefully I will explain the picture of what has been emerging recently, which is called the functional reactive front-end programming, or functional reactive programming as applied to front-end applications. So to begin, functional reactive programming is a particular application of functional programming, that is, programming with pure functions without any side effects, with immutable data values and usually strict types. However, these functions are now going to operate on values of a special type, which is to be described as streams of values. This is the only difference between ordinary functional programming and functional reactive programming. A very significant role is played by these data types, which are streams of values. Now, streams themselves are immutable. They contain inside them many different values, but as values themselves, streams are immutable. So we still are in the realm of pure functional programming, where there's a bunch of immutable data that is defined using pure functions. Computed, there is no mutable state, neither global nor local. These streams are at runtime displayed or used by the system. And of course, behind the scenes, the system can optimize this so that things are actually mutating. But from the point of view of the programmer, this is not happening. The program does not describe any mutation. The program is completely pure and functional. So that is the ideal of functional reactive programming. So the typical architecture of a functional reactive program is that there is a model, there is a view, and there are some inputs such as buttons or text entry fields. Now, in the functional reactive programming, we define streams of these values. So there's a stream that contains model values. There's a stream that contains the views or the values of the entire window that will be shown. So there are different views in the stream and different inputs in the stream as the user creates inputs. The program consists of functions that compute the input from the view. For instance, the view doesn't always contain the same input elements, and so sometimes some buttons are showing, sometimes they're not showing, and so on. And so in general, this is a function that computes the input stream from the view stream. But of course, the user supplies the actual values of the inputs. Then there's a pure function that computes the view from the model. And finally, there is a pure function that computes the model stream from the input stream. And that's all. That's the entire program. There are just, conceptually speaking, three pure functions that define three stream values in a mutually recursive way. So sometimes this situation is called the unidirectional data flow, meaning from the model to view to input and back to the model. So that is a terminology that is used sometimes. Now, while the program looks like a definition of some immutable stream values, the runtime library will actually display this to the user in a different way. So the stream of view values will be displayed to the user at different times as the new values are computed, and the runtime makes sure that this is done and that the inputs are collected from the user at that time and made into elements of the input stream. And so the model stream also will contain different model values at different times, which will be usually represented in memory by the runtime system, so that actually in memory there isn't a history of all models or history of all views, but only the one that is necessary for current computation. The values are cached, and but from the point of view of the programmer, this is invisible. The program does not know about this. This is the main point. So, well, from the usual view of programming, how do we do anything? How do we update anything if there's only immutable stream? Now, how do you change anything if you're not allowed to change? So streams replace this necessity for updating anything. Instead of updating a variable x, you make a stream of values which will contain all the necessary values of x eventually. And you define that stream as a pure function of some other streams. And then this definition and these computations are arranged just such that the stream of values of x will have actually the desired sequence of values. And if you look at them one at a time, it will appear as if they're updating. And this is what will happen at runtime. So the runtime system will make sure this happens, that they are computed one at a time, but as I said, usually the runtime library will make it as efficient as possible, so there is no memory leak in having to store so many different values in the stream that you don't need anymore. Usually it's very efficient actually, and also the views are cached. So if you imagine that there's a complicated view that is replaced by another complicated view, the runtime system will cache all the parts that haven't changed and actually change on the screen only small parts as necessary. But again, to the programmer, this is invisible. The programmer creates a stream of complete view values for the entire screen every time. From the entire model, which is, again, every time considered as one value.
So thus far, we haven't actually. What you're talking about seems to be relatively indistinguishable from the React system we have now, like with Flux, right? It sounds almost exactly the same. If you could kind of equate the event system that we use for stores to notify views that they've changed,
right,
as the stream,
right,
which conceptually you can. So basically,
yeah. So if you squint very hard, then you will recognize this scheme in React Flux architecture. You will not see you will see a lot more low-level detail that you have to write. But basically, I would comment on this a little later. But yes.
Okay.
So when you program with streams, you just write pure functions that use certain primitives, such as map, mapping stream values to get another stream by a function, or several streams that are in a list that are all maybe updating and you have a function that takes all of them and creates a new stream. So these are primitives that you have. So your program is a combination of these primitives and the stream and streams that are predefined for you. So this kind of programming is very high level. You do not talk about observing individual changes in the streams or reacting to a new value or anything like this. You just write a program that takes a stream, maps it over some function, gets another stream, merges with another stream, or there's scan. This is a very important primitive, scan, which is like a fold, except that it produces a stream of values. So it accumulates a B, modifies after getting an A from this stream, and gets a new value of B, and that's a new value in that stream. So this is like fold, except you generate all the intermediate values, and it's infinite. So yeah, I should have mentioned that all these streams conceptually are infinite. They never stop, because a typical user interface program isn't supposed to stop. It's supposed to be always ready for new input from the user. So conceptually, all these streams are always infinite. All right. So and here is an example of how you would update the model or pretend that you're updating the model. So you just say, you define an updater, which is a function from the old model value, input value, to a new model value. And this function is pure. It creates a new model value. And then you use this scan primitive with this updater. You give the initial model value and the input stream. And then you get the model stream. And that's all. So that's what happens in a pure functional reactive program instead of updating anything. And another interesting detail, just to see if I can use this. So suppose I have several streams and they are dependent on each other. They're computed from, so 4 is computed from 2 and 3, and 2 is computed from 1, and 3 is computed from 1, and 1 is receiving input from somewhere else. So what will happen if 1 receives an input? Then there are updates that need to be computed in 2 and 3. So then if you implement this with ordinary listeners, then what will happen is that 4 will receive 2 updates. Whereas conceptually you only wanted to receive 1 update. Something changed, so you want to update everything, but you don't want to update it many times, just because you have many intermediate steps in the update. So a proper stream library will do this correctly. It will not fire too many update events internally. So that prevents leaking the abstraction. So from your point of view, you are just really composing pure functions of streams. You don't think about when updates will be fired to what particular part of your computation. So that is how it's supposed to be done. Now, unfortunately, we don't have today a complete functional reactive programming framework. We have some parts. So React.js itself is not a full framework for FRP. It does this one part, which transforms the model stream into the view stream. And it caches the view stream after that. But it does not give you any way of defining the input streams easily or binding it to any model easily. That's your own business. So other parts were made, Flux or Redux, which we are now using. We're using all of this now, which are steps in the right direction. So what they do is they create a model and they give you the way a way of listening to updates to the model, so that from the model you get the view stream, and then it gives you also a way to sending updates to the model back from the view stream after some clicks or other input events. It does not separate the input stream as a separate entity cleanly, but it allows you to do pretty much the same thing. However, I would criticize these frameworks for being over-engineered. There are too many parts. For example, in the Flux framework, the actions, dispatchers, and stores, all those are basically parts that should be replaced with this clean abstraction of a stream of inputs, a stream of model. But they don't have this in particular because JavaScript does not support recursion when defining a value. So as I explained, streams of input, streams of model, and streams of view are three values that are defined by a mutually recursive expression, which is that model is a function of input, a view is a function of model, and input is a function of view. So this is a recursive value, which is something that most languages of that school cannot deal with. And so because you cannot deal with it, you have to put other things. You have to make more methods that update by hand, and so on. So that, unfortunately, remains with us as long as we are with JavaScript. Now, there is an attempt to make a language, a separate domain-specific language called Elm, to implement pure FRP. Now, that language is not yet production ready. Otherwise, I would have advocated it a year ago instead of doing other things, but it's not, unfortunately, very ready. And it also suffers from some over-engineering. It's basically not a... it's a learning curve, and it's not a big advantage over just using React with Redux or Flux. So right now, in terms of tooling, the best we can do for industry-ready development is, I would say, React with Redux, which is what Andrei started to use for the new player. Now, for this demo, I will be using some small libraries. I will be using React, but I will be using a stream library, which is called this. Now, if I try to pronounce this, I really wanted to pronounce this correctly, but I probably won't. So this is Flux. 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 Now, this is a word for flux in Danish. And this library is a library that gives you the streams, the values of type stream. I also use these two libraries for functional programming and union types. So let me just briefly touch on union types, since this topic might be of more wide interest. So I will be showing some demos using union types, and actually these are missing from many programming languages, such as C or JavaScript or, well, pretty much Java. Union types are motivated by the following consideration. So suppose we are modeling, let's say, a Minesweeper game. Now, in a Minesweeper game, we have the content of a cell, which could be either a bomb, or it could contain, it would be not a bomb, and then it will have a number of neighbors that you have to show. Now, how do you represent such a value? So usually people either use special values for bomb, so you have number of neighbors which is equal to -1, and that means the bomb. This is, of course, error-prone. What if you do computations with number of neighbors and you forget that -1 is a bomb, and you add -1 neighbors to something by mistake. Or you use a more complicated data structure, which is this, let's say, an object with different fields, and then if it's a bomb, that it will have a flag, is bomb equals true, and then 0 neighbors. Since you cannot exclude neighbors just when is bomb is true, you must have this redundant information, and again it's error prone. What if you only examine neighbors here? You don't know that it was a bomb, so you make a mistake. So disjoint unions represent this exactly well. So here's how I would explain them. So these are like enums, but with values attached to them. So here's an ordinary enum. Let's say it's a status of a request. It has success, failure, and pending values. This would be an ordinary definition of an enum. And then you would switch on it by writing something like this. So if you have 3 cases and then you do something depending on what cases it is. So the advantage of doing this is that you cannot make a mistake. Let's say if this were just a number 0, 1, and 2, then you could by mistake make it a number 5, which wouldn't mean anything. Here you cannot make this mistake. There are only these 3 values, and that's it. Now, an enum with attached values would basically look something like this. It would be a success with a response string value, or a failure with an error code and message, or a pending with no value attached to it. So that is what I mean by enum with attached values. And then you switch on it in a very similar way. If it's a success, then you have a function that takes a response string and does something to it. And if it's a failure, then there's a function that takes code and message and does something to it. And if there's a pending, there's a function that takes no arguments and does something. So again, here there's no way to make a mistake and to use a success value but extract the code and message out of it. There's no way to do it. The language prevents you from doing this. So that's the point of using union types. And the library that I use for this gives you a JavaScript interface that looks like this. So I can define success with a string, failure with an object, and pending with no value attached. And then I can create values of this type like this. And if I pass the wrong type, it will be a runtime error. And then I can switch on values of this type, and again, there's no way that I can make a mistake. It's basically exactly what we want when we represent a situation like this. And in situations with functional reactive programming where you have Inputstream, then very often you want a type like this. You want to describe different kinds of input and different states with values attached to them. And union types are very, very handy. So now I'm going to the demo. The first demo will be a program a web app that simulates a working day of a programmer in the following way. So I will show you the app. It's running right now. So when I make a cup of coffee, that adds some lines of code. I make more coffee. I am able to write more lines of code. And then finally, once I get more than 100 lines of code, I can commit it. So now I have committed it. I have no uncommitted lines of code. I need to get more coffee. And then again, I can commit it. So this is how it goes. So then finally, I get some lines of code here. and I can restart. So okay, so that is a sample app number one. So how will we code this? So we make a model stream. The model will contain the number of new lines of code, the total number of lines of code, and whether to show the commit button. So this will be our model. So the initial value of the model could look like this. We make an input stream. An input stream will have two possibilities: make coffee or push the commit. Well, there's also restart, but I omitted it from the slide here. So we define this union type that will have a make coffee and push commit values, and this will be the type carried by the input stream. So user click type. Finally, we bind this to React. I will show the code shortly. And finally, to update the model, we'll use the scan function, and all we need here is a pure function that will take the old model, the click value, and return a new model. So I will switch on the click value, and that's basically it. So let me show you the code. So this is the main application. This is a standard React application. There's nothing unusual. This is just boilerplate. The app looks like this. So it imports a lot of stuff from the model stream, the input stream, the functions that do coffee, commit, and restart. There's some boilerplate that associates the model stream with the state of the React component. And this boilerplate will be the same for all apps done in this way. And finally, I do a render, which is a function, pure function from model to view. So I use the state, how many lines are committed, how many lines are uncommitted. Then I check if I can commit now some more lines, and if so, I show the button. The button click functions are these, and these are basically little input streams that will be created when the user pushes the button. So then these are all handled in the model class, which I will show now, but that's basically the part that React does, computing the view out of the model, pure function. There's no update here, right? And finally, the model. Now, I made a point to write a constant keyword, which is a new JavaScript keyword. In fact, there's only constants in this code. There's no variable. There are no mutable variables anywhere. So this is the type of user click, which has restart, make coffee, and push commit. The user stream is created. Coffee, commit, and restart are functions that push events to the user stream, to the input stream. And then I have this function that computes the new model out of the old model, which is pure function. Very easy case statement that creates, adds lines of code if it's a push. Make coffee, then you add a random number of lines of code, and so on. And basically you check that the uncommitted lines are more than 100, then you can commit, and that's it. And then you have this boilerplate, which computes the model stream out of the input stream. That's it. That's the entire app. So you have the model stream, which will contain at different times these different values. When I do restart, it is changed. So the the model stream now contains the 0, 0, and so on. So that's all. Now, any questions about this? I'd like to then show the Minesweeper, for which I need to start it. So
they say,
yeah.
they say immutable. Sorry, I'm getting turned off by fancy camera here. Say that everything is immutable, and it seems like literally everything in the application is immutable, and that's made possible by these concepts of streams, which themselves are kind of mutating, but conceptually, even then, are not really mutating. So the whole app is in its entirety immutable. There's nothing that's mutable within the app at all.
That's right. Not in your code.
Right.
So there is no questions. You see, the advantage that it gives us is that at no time do you ask in your code, at what time am I here? Is it before that or after that that this function is called? It does not matter. The functions are called and they compute some immutable values, and that's it. There's conceptually everything is run only once here. You run this application once to compute these streams once, and that's it. So your code does not contain any place where the order of initialization matters, for example, because there is no mutability. So that is the advantage. There's of course a little learning curve to start thinking like this. But even even when you do React, you kind of think like this too. And the big advantage that we have noticed with React programming is due to this. What they call unidirectional flow is really just immutability. All right, so here's my Minesweeper. I'm going to boom. So what do we see here? We see a button. We see cells. We see this opening. We see the bombs. Right. All right. Now, if you notice, the bombs are in a very interesting pattern here. Now, this is because I cut some corners. I will show you now. They're always in a pattern, but so be it. Okay. So let me switch then to the Minesweeper. So again, Minesweeper is made in exactly the same way. There's a boilerplate for a React application. Then I have the React component, which it's frozen. All right. Well, let me see. Okay, it's done. So I have a React component that basically, again, is a render function that renders a model to the view. Now, in this case, the model is a bit more complicated. It is a board with cells, which is an array of rows, and each cell has a status, and each cell has a content, and then there's a button also. So there's a game status also, where the game status can be game not yet started, game started, and game lost. I have not yet implemented the win. So anyway, so basically this is just drawing the cells, and you see I use heavily this case construction where I choose what is the status of the cell, and according to that, I draw. So this is very kind of, this is easy to modify. So let me show you the model. So the model starts by specifying the types. So the cell status can be closed or open, which means shown or not shown. Content can be a mine, neighbors, that carries a number of neighbors. And then I have two other status values that I use just for technical reasons. It's equally easy to add more status values here. It will never break anything. There are no special number of neighbors or anything else like this. So in the functional parlance, this is type safe. My type guarantees that I don't make a mistake. Game status, playing, lost, starting. So then I specify, yeah, again, I made it a point that everything is a const. There's nothing else but a const here. There's no var anywhere. Const, okay, they're functions. I also declare them with a const, just to make a point. So there are some auxiliary functions. So what happens here finally is exactly the same thing as before. The game model is a stream that is defined as a function, as a scan function that takes the initial model, the input stream, and the function that makes the new model out of old one, given the input. Now the input can be user click on a cell, so it's a user click with two numbers, or it can be restart game, which has no value attached to it. So I use also the union type for the user click. I use union types for game status and for cell status and content. So there's quite a lot of assurance that all of this is safe. Now, it's not to say that it is not necessary to debug, but there are no stupid errors where you lost some little thing. So there is a little bit of type safety here. All right, so let me show you maybe what happens. So there's a first click. On the first click, okay, so where am I doing this? Yeah, if there's a first click, then I fill the board with random bombs, and if not, I don't fill the board. Now, filling the board, I took some shortcut, which is that I basically generate the indices of mines by arithmetic. So I have a big prime number, and I just compute some arithmetic expression, which is guaranteed to have different values for different mines. The result is that they're not really random; they're kind of in stripes. But anyway, this is just for demo. So you see, I'm using pure functional techniques. I'm mapping mines, and then I get that. I mean, this is an ordinary function. This is not a stream function. I use it in the stream, but everything else is an ordinary function. Reveal cell is a recursive function. I'm using a library called Ramda to do different functional stuff, but basically it's not really very important. I'm using lens, for example, which is kind of convenient sometimes, but anyway, this is not important. What is important is that I have exactly the same architecture. I have a single stream with model values. I have a single stream with input values. I define pure functions that compute model values out of input values, that compute view out of model values, and that's it. That's the entire app. So thinking about this app, thinking of what went wrong when something is not right. I mean, it is not true that I wrote all of this right away without errors. But when something is wrong, then I think about my algorithm. I think about my computation. What did I compute out of what? I never ask the question of, oh, did I initialize something? Or was it done too quickly before I initialized something? This is never the question. And that is the advantage of this kind of architecture. All right, so let me conclude by saying that pure functional programming is on the rise. Um, Everybody is using it, except for companies like Google. We should understand where the ideas come from. When we look at a framework such as React, Flux, and so on, it is very helpful to understand what these frameworks are trying to approximate. They're trying to approximate functional reactive programming. We do not have a full framework right now that would allow me to write such things more easily. But these frameworks are trying to approximate it. So those parts of the frameworks that are not trying to approximate it are not very useful. They are accidental. They can be changed. Those parts that try to approximate the idea of streams of data that are just transformed into other streams using a pure function, those parts are steps in the right direction. So for example, going from the Flux to the Redux library, in my view, is a step in the right direction. The difference between them is that the Redux explicitly tells you to make updating functions that take old values and produce new values and put these functions into your program explicitly. Whereas the Flux framework didn't talk about this. They gave you other things to do. So this, if anything, is a lesson for me from studying functional reactive programming. Well, thank you for your attention.